Alright, with today's video, we're going to take molecular geometry to one more level. We're going to learn something called hybridization and something called bond order. Both can be very difficult to understand, but also can be very easy to do. So I'm going to try to show it to you in a very simplified fashion. So up here I have the warm-up that we would do in class if we were face-to-face. So if you want to pause this video and see if you could do the Lewis dot diagram, the correct molecular shape, name the shape, tell me if it's polar, non-polar, and how many sigma and pi bonds, you can take that and do that. If not, so pause the video, see if you can do that. If you don't want to pause the video, I'm going to work through these because we're going to use these 5 as an example to learn bond order and to learn hybridization. Alright, so pause the video if you want to try this for yourself. If not, we're just going to keep rolling. So our first one is carbon tetrabromide. Carbon tetrabromide, and so that is a covalent compound. I know it's a covalent compound because it has a non-metal in the beginning and a non-metal. So covalent, non-metal, non-metal. I also see those prefixes. Those prefixes are dead giveaway that you're dealing with a covalent compound. So carbon tetrafluoride is just going to be CBr4. So I'm going to go to a blank page. So we're going to do carbon tetrabromide. So carbon and then tetrabromide. See, there's the formula for carbon tetrabromide. And so we're going to see if we can figure out what shape it would go into. See if it's polar or non-polar, see if we could answer those questions. So we do the valence electrons. Again, carbon is 4. Then bromine is 7 times 4. So I'm going to get a total. So this is 28 plus 4 is 32. Carbon goes in the middle, surrounded by, and I already know what shape this is going to go into, so I'm going to start it out in that chicken foot. I will tell you, just because it has 4, it doesn't always look like this, so you have to be careful. But you could start it this way, and then you might have to, if you end up with some lone pair of electrons, then you may have to correct yourself. So I'm going to give those each 8. So there's 2, and there's 4, 6, and 8. Go ahead. Ew, a little dot happy there. Sorry about that. So I'm going to give that one 8 because I've given 2, 4, 6, 8. 2, 4, and 6, and 8. 8 times 4 is 32. 0 extra electrons. This is the correct shape for that. I would look on here and I would say, okay, does it need any double bonds? If I'm drawing 4 bonds off of carbon, it will never need all your 4s, your 5s, and your 6s. They never need double bonds. So this doesn't need a double bond. And so this is what I call a 4-0. So 4 bonds in clouds. None of them are clouds. Remember, this is total bonds in clouds, and this is the number of clouds. And the 4-0 is always known as tetrahedral. That is the name. You do need to memorize the name of the shapes. So you do need to memorize the name of the shapes. Alright, tetrahedral. That is the geometric name for that. Alright, and this is the correct shape. Let's do sigma and pi bonds. So this is going to have 4 sigmas and 0 pi bonds. This shape is non-polar. It's pretty much even all the way around. So these are questions that you would have to ask or answer on a test about the compound. So 4 sigma, no pi's, tetrahedral shape. Alright, so we're going to go on to the next example. And our next example was silicon dioxide. Silicon is Si, dioxide O2. So silicon is 4, it's in that carbon family. Oxygen is 6 times 2. If I add those together, I'm going to get a total of 12 plus 4 is 16. So I would put Si in the middle, surrounding by a couple of oxygens. I would give those outside guys their 8. Outside guys have their 8. 8 plus 8 is 16. So no clouds involved in this one. No clouds. Don't even have any extra. Clouds are the extra ones. There are no extra ones. Now I need to decide, once I know that there's no clouds, that's important, always figure out if there's any clouds first. If there's no clouds, I need to see if silicon has 8, and it only has 4. So I'm going to take away 2, and I'm going to draw a double bond. Does it have 8? Nope. So I'm going to take away 2 and add a double bond. Now you could have made a triple bond and a single bond. That has something to do with formal charge. We are not going to do formal charge, so we're not going to worry about that. So doesn't that just look better? So if they're the same elements, it probably will double bond, double bond. All right. As far as the shape is concerned, remember we look at sigma bonds. Let's go ahead and do this. We have 2 sigma bonds, and there are 2 pi bonds. As far as shape concerned, we only looked at the sigma and clouds, and there are no clouds on the middle guy. So this is what I would call a 2-0. The name of a 2-0 is linear because the elements are all in a line there. And this is a non-polar shape. It is nice and even. It's always going to be even if these 2 elements are the same. If this had been maybe fluorine and this had been oxygen, they would not be the same and it would be polar. Remember, polar means not even. Alright, so our next example, we're going to come back and we're going to do something with those. This is just a review of last lesson. And so our next one is selenium dioxide, so SeO2. And a lot of times students want to make this one look just like this one because it looks like, oh, well, that should be the same. No, that's when we have to add up those electrons. So this selenium is a 6. Oxygen is also a 6, but times 2. And you got 12 plus 6, you get 18. Can you already see that the totals are not going to be the same? So we put Se in the middle. We give those outside oxygens their 8. Okay, there's 8, 8. 8 plus 8 is 16. There are 2 extra electrons. See, up here there was an extra electron. This one has 2 extra electrons. Extra electrons are the clouds. So I'm going to draw a cloud up here. This is going to not end up, I should have went ahead. This is going to go ahead and bend. I should have went ahead and put it in the correct shape. Let me get that going. Should have done that. I knew what shape that was going to end up in. Alright, you didn't. Remember the first one is a rough draft. But alright, so 8 plus 8 plus 2, there's 18. So now I've taken care of all the electrons. So once I've taken care of all the electrons, I've given out, distributed them, and then gave out the extra. I look at selenium. Does it have 8? It has 2, 4, 6. So remember, if it doesn't have enough, now you got to take away and draw a double bond. Okay, so this is not a sigma bond, so this has 2 sigmas. Remember, the sigmas are the initial ones. I'm going to highlight those in yellow. So those are the sigma bonds. Go ahead and do it here as well. Those are the sigma bonds. And then these are that's the pi bond in pink. I've gone there. Pi bond there. Okay. Let's see what else we can answer about this. So two sigmas, 1 pi. And because of that lone pair of electrons, it doesn't have anything to counterbalance it. This is actually a polar molecule. Polar molecule. And then for shape, we again count the sigma, so there was 1, 2, and the cloud. So this is what I call a 3, 1. That's the total of sigma and clouds, and that's the number of clouds. What was happening, it wanted to look like that, but this cloud bent it. So this is called bent. It is a bent shape because it bends it. I probably bent it a little bit more than it needed to be bent. Alright, on we go to 2 more. We've got NO3 negative 1, that is nitrate. That is my favorite polyatomic. So NO3 negative 1. So we would add 5 for nitrogen and 6 times 3. And then I do opposite whatever this sign is, -1, I add 1. So that's 18, 19, so I have a total of 24 electrons. So nitrogen in the middle, I'm going to go ahead and put it in the shape that I think it's going to be in. Hopefully it'll stay that way. It will. So we've got 3 oxygens, and I would give them their 8. 8 times 3 is 24. 24 minus 24, no clouds. See that? No clouds. No clouds on this one. So now I need to see if the middle element has 8, and it only has 2, 4, 6. Can't do clouds. So last thing you do is double bond. So double bond, doesn't matter which oxygen. Because I'm putting it on this one, but it really could have been on that one or that one. That's going to mean something in a moment. All right. This is ions, and we put brackets around it so the polarity doesn't matter. So as far as the sigma bonds are concerned, there's 1, 2, 3 sigmas and 1 pi. 3 sigmas and 1 pi. So 3 sigmas and 1 pi. I guess I should stay consistent. I was writing the pi symbol. Either one. There we go. And as far as polarity, that's not applicable. That's actually what I put on your test in that box. I would put NA, meaning you don't have to answer that question. As far as the shape is concerned, remember it is the sigmas and the clouds. Not worried about the pi. The pi's don't make it a different shape. That's just like double bonding. It's just like a stronger. So 1, 2, 3. This is what I would call a 3 and no clouds. 3 sigma clouds total. That's a total. And then this is, because the clouds do cause shape problems. And so this is called trigonal planar. And again, you do need to memorize the names. Okay. Last one. We're going to look at xenon difluoride. Xenon difluoride, which is XeF2. Xenon is about the only noble gas that I know of that really bonds, and it likes to bond to fluorine. It will share with fluorine because fluorine is so electronegative, it can bond to xenon. So those are some compounds. Xenon tetrafluoride and xenon difluoride are some compounds that do exist. Alright, so xenon valence is 8, fluorine is 7 times 2, so it's 14 plus 8 is a total of 22 electrons. Xe in the middle, going to surround it by some fluorines. I'm going to give those outside guys 8. 6 dots in a line. 8 plus 8, 16. 22 minus 16 is 6. There are 6 electrons left over. Okay, so what does that mean? That means you're going to have 3 clouds. 3 clouds going on here. 3 clouds. Crazy deal. 3 clouds. So I just gave out those 6, so now I'm at 0. Now we need to see if xenon needs double bonds. Clouds count, so it's got 2, 4, 6, 8, 10. It's okay to have 10. We do not double bond if it's got 10. We only double bond if it's got 4 or 6. Okay, so or even 2. So no double bonds needed in this. So the things around it, this is what we call it. 5, 3. 5 total sigmas and clouds. Number of clouds, 5, 3. Okay, total number of clouds, 5, 3. And this is actually also called linear. The reason it's called linear is because the elements themselves are actually in a line. Now I've drawn this 2D, but the angle between here and here and here are all 120. So they're actually evenly distributed throughout. So they're even though my drawing doesn't look very even. Okay, so I'll show you the 3D model here in a moment, but those are even, which is going to make this a non-polar molecule here, because even though it doesn't look even, those are actually evenly going around. Alright, and there are 2 sigmas and 0 pi bonds. 2 sigmas, 0 pi bonds. Alright, wrong color. So that's what we did last time. So now we're going to do bond order. So we're going to come back and we're going to figure out the bond order. So I'm going to go to the slide. You can take and copy this for just a second. So first thing you're going to do is draw the structure. We just did that. We drew the Lewis structure on them. Find the correct number of sigma pi bonds. You're going to count the total number of sigma pi bonds, and then you're going to divide by the number of bonds that have atoms to it. Here's an easier way to write this. To find bond order, you're going to take the sigma bonds plus the pi bonds. That goes on top, and you're going to divide by the number of sigma bonds. This is the easier way to do it. It's technically supposed to be the number of atoms, but atoms initially are bonded by sigma bonds. So total bonds has to be bonds, not clouds. Sigma and pi bonds divided by sigma. That's going to get you the bond order. Alright, so we're going to figure out the bond order for each one of these, and then it's just going to be a number, and then I'm going to show you what that means. Alright, let's go back to, so sigma and pi divided by sigmas. So here we would have 4 plus 0 equals 4. That's our total. And then it's divided by sigmas 4. So this has a bond order of 1. Okay? I'll explain what that means in a moment. So this is bond order. On your test, you'll have to figure out what the bond order is for. So this is what we're doing here, bond order. So down here, on top is the total. So 4 plus 4 is, 2 plus 2 is 4. My brain going ahead. And then it's divided by the sigmas. So this is total. And then 2. So this has a bond order of 2. Bond order of 2. So then this one, 2 plus 1 is 3 divided by 2. And we're going to go ahead and do this as 3 divided by 2. You can do it in decimals, so you can do 1.5, or you can say 1 and a half. Either one. I don't want you to leave it in that form though. Do not leave it in that form. So 1.5 or 1 and a half. Okay? Look at this one, and then we're going to explain what this means in a moment. So if I add these together, the total is 4 divided by 3. You get 1 1/3, so 1.3333 repeating. You don't even have to put that. You can just do 1.3. I'm fine with that. Or you can go 1 1/3, either one. And if you need to, you can put that in the calculator. But back in elementary school, we learned how to make those improper fractions proper fractions. So hopefully you were taught that as well. All right. So then this is 2 divided by 2 equals 1. So this has a bond order of 1. So that's how you calculate bond order. So now let's talk about what in the heck that even means. All right. So bond order of 1 means that each outer element has a 1-to-1 direct share with the center atom. That's what bond order of 1 means. It means this carbon has 1 direct share with each of those. So it only has sigma bonds. So this carbon has 1 direct bond here, 1 direct. So its ratio is a 1 bond to the center atom. Okay? It'll start making more sense as I go on. So look at this. do you see each of these oxygens? They each have 2 bonds that go out. They have 1 sigma, 1 pi. So this is called a bond order of 2 because they each have 2 bonds. Bond order of 2 there. Next one. The pink bond that I drew there. I drew it on this oxygen, correct? But couldn't I have drawn it on this oxygen as well? I could have. I could have drawn it on this oxygen, or I could have drawn it on that oxygen. Really what it is, and I don't want you to do it this way, but what's happening is it's really not that one or that one. It's kind of like on both of them. It's kind of like that. We draw it on just one, but it's really kind of being shared between each one. So let me put it back, the pink that I had up there. So I drew it here. So do you see the yellow? They each have their own one. That's this. They have each their own individual bond, but the pink guy is actually being shared by 2. So if one thing is being shared by 2, you kind of each get a half. So that's why it's 1 1/2. They each have their own 1, and the pink guy, they're having to share among the 2 of them. That's why we say it's a 1 1/2 bond. Next, look at this. They each have their own 1. The pink guy, really I drew it on this oxygen, but I could have drawn it on that oxygen or that oxygen. So that double bond, that pi bond, is actually somewhere in between all 3 of them. So they're having to share it 3 ways. So they each have their own sigma, and the pi is being shared amongst 3 of them. That's 1 1/3. Make sense? And on this one, each fluorine has their own sigma bond. We don't care about the clouds. The clouds are not bonds, and so bond order, we don't care about clouds, okay, because it's a bond. A bond is between 2 elements, and the clouds are just clouds that are messing up the shape, what's happening here. So they each have their own one, which is why that. So if you only have sigma bonds, your bond order will always be 1. You only get the weird numbers if you start to see pi's, okay? So that's bond order. Hopefully that makes sense. That wasn't too bad, was it? All right. Our next thing is called hybridization. Hybridization, it looks crazy, but I promise you I'm going to make it super easy. If you want to confuse yourself, Google it. You'll watch all kinds of weird videos. I'm going to make this painless, I hope. Okay. Hybridization basically is a blending. If you know what a hybrid is, if you've ever taken a biology class and you've talked about white flowers and red flowers and they cross them, they can make a hybrid and they get a pink flower. So a hybrid is basically a blend, kind of like a hybrid car has gas or electricity. They don't blend the gas and electricity, but it runs off both. So it's a blending is what it is. So that's all it is. And so what happens is when an atom gets ready to bond, do you remember they have those S's and those P orbitals and they have those D orbitals? Well, that center atom, sometimes when it gets, well, not sometimes, when it gets ready to covalently bond, those S and P areas, and sometimes D areas, are no longer distinct. Here's the drawings. Here's an S, here's some P's. That's what they look like when we were looking at them. I didn't make you draw them or anything. They're crazy. But when it gets ready to bond, these guys start blending together. And so no longer does it look like an S, no longer does it look like a P. It's called an SP, is what it's called. So it's a blending of shape. If you don't quite understand that, that's okay. We're not going to draw them, okay? So just understand it's a blending of the orbitals. And so here's what an sp3 orbital looks like. It's a blending of the shapes there. So, all right. I'm going to go to a blank page. So, do you remember when we were doing the arrow diagram? And so we had the S's, and for the S, I said you could draw one blank. Remember we did that. those were electrons. Okay, so, but the number of blanks that we drew, well, I can do that. That's okay. Let me go back. So the number of blanks that I drew for the S, well, I just drew one blank. For the P, I drew 3 blanks. Remember, they could hold 6 electrons. That's the arrows. Okay, but these blanks were the orbitals. The blanks were these crazy things. So this was 1, and the P's had 3. So these crazy things here, we use blanks instead. Okay, that's going to be important. We're going to be thinking about those blanks. So, whoops, went the wrong direction. And then on the D, it could hold 10 electrons, but we had 5 blanks because it had 5 weird shapes. 1, 2, 3, 4, 5. And then the F's, not that we're going to get into the F's because we don't see the F's involved in the bonding, but there would be 7. But I'm not really worried about the F so much. Alright, so what happens is when an atom bonds, we get a blending of these. And so when I keep saying the best way to memorize these is saying like 2, 0, 3, 0, 3, 1, that stuff, and we're going to look at that in a moment. This is the number that I'm going to be referring to. This is the how many bonding sites that I need. So that's how many orbitals are going to blend. How many orbitals are, I'm going to go ahead and put the rest of the chart down here. This is the chart. And that I have that worksheet. Let me go ahead and I'm going to get it down. These are the ones that you need to know, and there's a lot of them, so but you've got some time to study. Okay, so that is the whole chart. What in the heck are you doing, Miss Smith? So that's this, the 2, 0, 3, 0, that chart. That's what I'm referring to. Okay, so I just have it there. So I want to focus in on that number right there. That number is how many blending sites you need. That's how many things will hybridize to get me 2 spots for bonding. Okay, so I need 2 spots. So if it's a 2, it's going to need one of these and one of those. So if it is a 2 something, which is linear, by the way, the name of it is linear, the hybridization needs to have 2 things. It has one S and one P to give me 2 spots. So anything with a 2 hybridization has an S, one S, and one P hybridization. This seems hard, but I promise you there's a pattern, and it is actually super easy. Alright, the things that are 3. The 3, 0 is called trigonal planar. Scoot you over a little bit. Okay, the 3, 1 is called bent. So these are the names, and I would tell you to kind of learn this. Okay, but both of these have 3 spots to hybridize. 3 things are going to hybridize. So both of these have the same hybridization going on. But I need 3. Well, I only have one S, and I need 3 spots. Well, there's one P, so it needs 2 of these P's, 1 of those and 2 of those. So we say it has one S hybridization, and you're welcome to put 1, 1 if you want to do that. We just tend to don't put 1s. And then it's going to need 2 of the P's. This doesn't mean 2 electrons. This is just telling us how many. So basically it's like this. This is 1 S and 1 P. This is 1 S and 2 P's that are getting hybridized. That's another way you can write it. This is the way we simplify it. And I would actually prefer you to do it this way. So both of these, the hybrid, if I ask for the hybridization, because it's a 3, you would say it's 1 S and 2 P's. Can you see that that equals 3 there? 1 S and 2 P's. Alright, these guys that are 4s, 4 zeros called tetrahedral. 4,1 is called trigonal pyramidal. 4,2 is also called bent. It looks shaped very similar to this one, so you got two of them called bent. But they all have 4, which means I need 4 bonding things to blend. Well, I'm going to need all of these. I'm going to need 1 S, and I'm going to need 3 of the P's. So 1 S and 3 of the P's. Or you're welcome to do it this way. Okay, that is another way that this is the correct way. This is just to help you understand it way. Okay, so now 5. Let's see, we'll get the names of those in just a second. The 5s, I need 5 spots. But look, on the P's, they're gone. Whew, this thing is not wanting to move on me. So for the 5s, I need 1 S, 3 of the P's, and now I'm getting into the D's, which is why the thing can have more than 8 electrons, because now it starts putting things in that D sublevel. So it has 1 of the S sublevels, 3 of the P sublevels, and now we get into the D sublevel. So it looks, whoops, did not do that right because I'm not used to it. So it looks like that. That's what's happening there. This is the way we write it. If you want to put 1s there, you're welcome to it. Can you see that equals to 5? That's the hybridization. The hybridization. All right, let's name these guys. So the 5,0 is called trigonal bipyramidal. It looks like 2 pyramids stuck on top of each other. Whoa, can't spell. The 5,1 is called seesaw, and it looks like a seesaw. I'll show you that. The 5,2 is called T-shape, and the 5,3 is called linear. Those are the names of those. I'll show you why. All right, 6. Go back to here. I need 6 things. I'm going to need 1 of the S's. I'm going to need 3 of the P's. And I'm going to need 2 of those D's blending together. And that's going to give me space for 12 electrons. So believe it or not, so 1 of the S's, 3 of the P's, and 2 of the D's. sp3d2. That is the hybridization for all the 6's. So 6,0 is called octahedral. Remember, it's called octahedral because if I close in the sides, it would look like an 8-sided figure. The 6,1 is called square pyramidal because it's a square-based pyramid. The 4,1 is a triangular-based pyramid. This 6,1 is a square pyramid. And then 6,2 is called square planar because it's a square in a flat plane. All right, you do need to know these names, and this is the hybridization for those. All right, we're going to go back to that warm-up that we did and see if we could figure out the hybridization for those. Let me go back, find it. Okay. It has to do with this number right there. That's where it means. That gives you the shape and the hybridization. It's a 4, so it's going to need 1 S and 3 P's. S's only go to 1, P's go to 3. This is going to need 2, so it's going to take 1 S and 1 P. This is called the hybridization. Okay. This is a 3, so it's going to take 1 S and 2 P's. That is the hybridization. That's what's blending in the middle element. Those of you that go on to take organic, I know that many of you are, you will use hybridization for your organic compounds. And it's going to be based on the carbon atom. Alright, this is going to be a 3. So 1 S and 2 P's. And then this one is a 5. So it's going to be 1 S, 3 P's, and 1D is the hybridization for that one. All right, so I've got some pretty pictures here. That's got pretty pictures too somewhere. Here we go. So this is showing linear, so 1S and 1P. So 2SP. The 2 is just saying what I had with that, like 20 and stuff. SP3, so SP2, sorry, 2S and 2 P's. SP3, SP3D. And that's some pretty pictures of how they look when they're hybridized. And the 6s are SP3D2. And then also on your little sheet. So if you printed this off, see the 2s? There's the hybridization. Here's the 3, SP2, SP2. The 4, SP3. Here is the 4, SP3, SP3, SP3. And whoop, here's the 5s, SP3Ds. And then we've got the 6s, SP3D2s. And those are all those names that I was writing on there. So I wanted to show you why that XE F2 was nonpolar. That picture is a little bit better. Oh, I've cut it off though. It had another ball down there. Okay, so can you see that those are all the way around? It is, these are 180 degrees, but the angles between this, again, 3D versus 2D, you can't really tell, but all the way around they're even, which is why that is nonpolar. All right, I do want to show you one last thing, and this is up under the Unit 2 homework. This is how it will look on your test. So your test will have blanks like this where you're going to be putting in the name of your geometric shape. You're going to tell me if it's polar or nonpolar, how many sigma pi bonds, the bond order, and the hybridization. So you'll be filling all this stuff in, fill in the blank part of your test. So I would suggest the answers to this are up, so I would suggest you kind of use this to practice for your test. I'm going to do this one with you and then just show you how it would go in. So this is very similar to that note page. So I'm going to add up, so this is 5, and then hydrogen is 1 times 3, so I have 8 total. Okay, so I'm going to put nitrogen in the middle. And remember, hydrogen can only have a line to it. We don't put dots on hydrogen. So I'm going to go ahead and draw a line to hydrogen, because I know the shape is where I'm going with this. So I would go ahead and I'm drawing it. This would be a rough draft. It didn't have to be drawn correctly. Here's where you would draw it correctly, but I'm going to bypass this one because it's going to be, so I've given 2, 4, 6 electrons, but I have, board's cutting out. I guess it's getting tired. Okay, so I've got 2 extra electrons, so I'm going to have a cloud. So this is what I would call that 4-1. 4-1. The 4-1, the name of the shape is trigonal. And this doesn't need a double bond because he has 8 around him. This is going to be trigonal pyramidal. Trigonal pyramidal. It is polar, and you're welcome to on your test just put P. P for polar and NP for nonpolar. I am fine with that. This has 3 sigma bonds. It had some clouds, but I'm not asking you to do the clouds. And no pi. It has a bond order. Well, it would be 3 divided by 3, so it has a bond order of 1. And the hybridization needs 4 spots, so it needs 1 S and 3 P's. So that's what you would be putting on your test. And that is the correct drawing, so that would have gone there. Okay, so I just went ahead. So the answers to this are up online so you can check and practice. And then Kim 101's course got some good practice for you as well. Alright, hopefully if you need me, you will email me and let me know. Have a great day.